Okay, it's time to start. Good afternoon, everyone. Good morning, good evening, depending on which part of the world you are at this moment. So welcome to the fourth in a row webinar from RAS organized. My name is Nikola Bešinović. I'm from TU Delft University of Technology from the Netherlands. So we have an honor to have a presentation from Tyler Dick from Rail Transportation and Engineering Center at the University of Illinois at Urbana-Champaign, where he's a lecturer and a principal research engineer. So the topic of today is network efficiency cycle, quantifying yard and mainline railway capacity and performance connections. So what we see commonly today that many researchers focus on one part of the railway puzzle, either on main lines or yards independently. But instead, this presentation will address the connections between yards and main lines and their critical interconnectedness. So before we start, I'd like to ask you to turn off your microphones, and we'll have the 30-minute presentation by Tyler first. Afterwards, we'll have questions and answer session. And I would invite you to type your questions in chat, and I will read them to Tyler afterwards. And for the ones interested for recording, we'll have it afterwards together with slides, and we'll share it after the webinar. So that would be all from my side. We'll invite Tyler to take over the lead, please.
All right, well thanks, Nikola. Thank you for that introduction, and it's great to see everybody virtually online. Thanks for joining us today. As Nikola said, I'm going to be talking about the concept of the network efficiency cycle and what we can do to potentially quantify connections between the capacity and performance of railway main lines and yards and terminals. I'm going to start by briefly reviewing some of the capacity and performance factors, how we define capacity and performance for main lines and yards, and talk about some of the challenges of connecting them. And then I'm going to move on to briefly review some of the results of some different experiments that we conducted here at the University of Illinois to try and quantify some of the interactions between yards and main lines. And then just summarize, bringing that together and talk about how that affects the overall performance of the rail network as a whole, and sort of pose the challenge of how do we improve our tools to better capture these connections in the future. All right, there we go. All right, so just for those who are not familiar with the freight rail transportation network in the United States, each year the U.S. Class 1 freight railroads transport approximately 1.7 billion tons of freight. And as for-profit enterprises, there's a strong financial incentive to match the capacity of the freight railway network to meet this transportation demand. And within the United States and really the broader North American context, there's an integrated rail network, and it consists of over 161,000 miles of track, and those are organized principally into 94,000 miles of mainline corridors. But we also can't forget that there's hundreds of yards, terminals, and junctions that serve as the nodes on that network. And those yards and terminals have a very important function because each day on the US freight rail network, those yards and terminals are the locations where we bring together approximately 1.5 million freight cars and over 29,000 locomotives, and form approximately 5,000 trains that depart their initial yard or terminal each day. And then similarly, those 5,000 trains arrive at their destination And it's at these yards and terminals that they're disaggregated into their individual rail cars and locomotives that then move on to their next shipment or next assignment. And so it's a very complex network, and defining the capacity of this network is quite the challenge. And what we find is that main lines, yards, and terminals all contribute to the overall performance and quality of railway service. So for example, here, if we have a shipment moving from an origin point A on the left-hand side of the screen, or a loading terminal, going to a destination or a loading terminal point B over on the right-hand side of the screen, we may have several different trains involved in that movement. We have a local train that transports that shipment to a classification yard, where it's sorted into a block that then moves on a manifest train, and that manifest train that carries rail cars for different ultimate destinations may visit several different classification yards or a block swapping yard on the way to a final classification yard near its destination, whereupon it's sorted again and then makes a connection to a local train, which ultimately delivers that rail car to its final destination. So we can see that the overall performance of this trip plan through the network, it's not just a function of the performance or speed of the manifest trains over the mainline links, but also on the quality and efficiency and timeliness of connections that are made at these different classification yards on the trip between A and B. So the objective of some of the research that we've been looking at in recent years here at the University of Illinois is trying to develop a stronger fundamental understanding of railway classification yard capacity and performance, and how it connects to this capacity and performance of railway main lines, particularly under the context of flexible operations that we have in North America.
Hey, Tyler.
Yes?
If I may. So a number of the North American Class 1s have intermodal unit counts that are approaching 50% of their total volume. Your manifest-centric depiction on the slide before is not inappropriate to the intermodal, operations either. I mean, it's a framework that can be applied there with intermodal hub, substituting for your origin and destination serving yards. Right. And really, you're acquiring units from and releasing them to the outside environment at those loading and unloading hubs. But otherwise, I think the analogy works. And at some point in the future, I'd like to see the intermodal centric version of this.
Okay, well, thanks, Marty. That's a great comment, that just because I've depicted this in a carload freight type environment, it still has applications to intermodal service as well, which is of course very important for the U.S. freight rail network, and is sort of the number one source of revenue now for the U.S. Class 1 freight railroads.
And also where it's taking place. If we're going to have this applicable 5 years from now, when intermodal is an even larger percentage of the total units, at least in North America, you're going to be pushed there by market changes.
Okay, so I left off in this concept of a flexible operating environment in North America, and that poses a unique challenge for, particularly with the audience, that international audience we have on this webinar. Is there's a large body of international research available out there, but most of it's focused on the environment, what we call structured operations. So this is typically where we have a fixed timetable that's planned well in advance, and it has resolved train conflicts. And there's a number of standard approaches we can use to calculate line capacity within that context. For example, the UIC has their compression method, which is a well-known way of estimating line capacity. And predominantly, this is applied to multiple track main lines, and predominantly on networks that are dominated by passenger operations. So the little time distance diagram there at the bottom left kind of depicts this environment where we have a fixed departure time. We have a fixed running time because we have pre-planned meets and resolved conflicts with other trains. And we have a fairly fixed or predictable arrival time at a final destination. And it's difficult to apply this concept and the resulting sort of body of capacity research to North American operations, where we have what's been called flexible operations. We predominantly have a single track main line and freight trains, and we don't have a fixed timetable so much as we have a train plan with target departure times and some degree of schedule flexibility. So if we have a comparable time and distance diagram, we have a train plan, may not always hit that departure time. So we have some sort of a flexible range of departure times. And then because we don't have pre-planned meets on the main line, we have a rail traffic controller or a train dispatcher that's resolving conflicts between trains in real time. We have some sort of flexible running time. We don't always have a consistent running time between origin and destination. And the result is we sort of have this range of train paths between a flexible departure time and a variable arrival time at our final destination. This has been called flexible operations. So this makes it difficult to apply this vast body of capacity research to our operating context of North American freight operations, predominantly on single track. So how we sort of define mainline performance and capacity is we look at several different mainline performance metrics. Two of them, for example, one is train delay, where we compare the actual train runtime to the minimum or best achievable running time for a train as if there were no other trains available or no other trains present on the network. So what's the best possible we could achieve while obeying all speed restrictions? The difference between that and the actual train running time, we call that train delay. We can also look at average train speed, which is a metric reported by most of the Class 1 railroads on a regular basis, where we take the total train miles of trains operated across the network and divide by the total train hours, excluding all the time in yards and terminals, and we use that to calculate an overall average train speed. And what we can do is we can look at how these different performance metrics vary with volume in terms of trains per day moving across an individual segment or corridor or network, and use that to define our capacity. So at the bottom, we have some example curves of what these relationships typically look like. As we increase our volume in trains per day, we tend to have an exponential increase in our average train delay. And similarly, as we increase our volume, we tend to have sort of a decay in our average train speed. And the way we typically define capacity is we set some sort of maximum allowable average train delay, and where that intersects our delay volume curve, we define that as our maximum volume or capacity that's practical for moving across the network. We can do the same thing on our average train speed. We just set a minimum average train speed, and when we have a volume that decays to that point, we use that to define our maximum volume or capacity. So quite a bit different procedure than what we do in a structured operations, where there's a much more formal process of analyzing that timetable to calculate line capacity. On the yard side, we have a similar concept where we just use some different performance metrics that are more applicable to the yard environment. We can look at the average railcar dwell time, so the average time a railcar spends in the yard from arrival to departure. We can also look at the number or percent of connections achieved. So that's the fractions of railcars that depart on their intended train. And we can also look at the departing trains, the on-time origination. So the fraction of trains that depart at the planned time, given that we just have a target departure time for a train departing a terminal, and we don't have that fixed timetable of all of our points along the route for that train. And the same way we do this on the main line, we can also define yard capacity by setting a maximum limit on these performance metrics and looking at the volume in rail cars per day moving through that yard. So we tend to see an average or exponential increase in dwell time for a given volume. We set a maximum allowable average dwell time. We can convert that into a maximum volume for that yard. Similarly, we could look at, again, we have a decay in on-time originations as our volume increases. We could use that to also define our maximum volume and capacity for our yard. So those are two sets of independent performance metrics that we have for main lines and yards. And when we go look at planning research or doing planning or modeling our network, we have this series of disconnected modeling tools. We tend to have models and simulation models or different sort of analytical tools to analyze the main line, mainly within the North American context, looking at the meet and planning process of trains operating on single track. We have a separate set of tools that we can apply to yard operations, whether that's a simulation model or a queuing model or some sort of analytical approach to analyzing the yard operation. And similarly, we have also network models that take this all to a much higher level. And one of the problems when we look at what kept tracking the interactions between these different tools is that they're all disconnected. They don't really consider each other in their modeling and simulation process. So if we look at our main line and yard terminals, At the ends of the main line, where we should have a terminal, we really just have a black hole where the trains disappear to. We've sort of got infinite capacity to absorb or generate trains moving in and off our main line. Similarly, most of our yard models, the main line is effectively equally a black hole. We can always absorb trains onto our main line. We can always generate trains from the main line as well. And when we look at a network model, these detailed operations of our main line and our yards are really abstracted into some fixed node costs and capacities, or a fixed link cost and capacity. And that works well for a lot of traffic assignment and planning models, but it doesn't really capture some of the interactions between the links and nodes. The node doesn't adjust when the links around it get congested. Similarly, the links, their costs and capacities don't adjust when the node gets, approaches its capacity when you're looking at a network model. And typically those are either fixed costs or very simple linear models that potentially adjust those costs as volume, just to make the modeling simple at the network type level. And then said, as they don't really capture the interactions between the different nodes and links on the network. So one approach that's been proposed to better capture those mainline and yard interactions is something called the network efficiency cycle. And this is something that Jeremiah Dernberger somewhat documented in his master's thesis back in 2006. And I kind of had taken his concept here and presented it a little bit differently and adapted. And it's this idea that we have a flow of trains and resources between the mainline operation, which is sort of the upper half of this cycle on the screen, and our yard operation, which is down at the lower portion of the screen. And the idea is, if we have some disruption in our mainline operation at the top, that can potentially delay train arrivals at our yard, okay, which potentially disrupts our yard operation, potentially disrupts the flow of rail cars into our yards, the flow of inbound locomotives, the flow of inbound crews to our yards. And once we disrupt that operation, we sort of disrupt the outbound flow of departing trains from that yard. And when we do that, we potentially can further disrupt our mainline operation, which can reduce its efficiency and reduce its mainline capacity, again, reducing our average train speeds, which again delays trains at the next yard. So that's sort of the main outer loop of this network efficiency cycle. And potentially we've sketched in some additional feedback loops on the inside. So for example, if we reduce our yard capacity and have some sort of congestion, that potentially has a feedback effect of, once the yard fills up, you've got to delay trains on the main line because you've got no place to put them in the yard. Once you delay trains on the main line, you're reducing your average train speed, you're potentially taking away capacity. And if the main line fills up and doesn't have that capacity, another terminal upstream may have to further delay their train departures, which creates further congestion in the yard. And you potentially have this feedback cycle moving along inside the loop on the inside as well. And so Dernberger sort of proposed this network efficiency cycle as a way to potentially connect the operations of the main line to the operation of the classification yards that serve as the major nodes in the network. And if we look at over time, what we've done is most of our body of mainline capacity research focuses sort of on this upper portion of the loop. What's going on in the main line, and what does that do for train delay, and how does that correspond to trains arriving at terminals on the main line? And so most of our past research or academic effort, most of our railway industry analytical effort has been focused on this mainline capacity and performance. And if we go back over the past 30 plus years, there's really been very little done in the yard capacity area.
May I interrupt you?
Even less done to...
Milan Janic from Ljubljana. I'm sitting here, and former Nikola's colleague from TU Delft. What is the reason that body of mainline capacity research is there and the very little research has been devoted to the yard capacity operations, management of, let's say, classification of trains and so on? What have been the main reasons? Have been the main reasons the lack of interest in the researchers, or the lack of needs from the industry? Can you say a word about that?
There's a variety of different perspectives on that. one of the other things I think that's important to think about when it comes to yards is the challenge of creating very general yard models. A typical main line, even though they may look different, you may have different siding spacing and distance and lengths of sidings and distances between them. They all sort of ultimately have somewhat of the same function of trying to move trains efficiently as possible from one end of that main line to another. Yards and terminals become very, very site specific. It's hard to come up with a very general yard and terminal model, and each one has sort of individual and specific processes, which can be quite different and more complex and interact in terms of defining its capacity, I think. There's a lot of specialized operations in each terminal, and the layouts are different, and it's much harder to capture a general model within your yard and terminal space. So that I think is one of the obstacles to coming up with some generalized yard and terminal research, and one of the challenges that's led to less work in that area. Okay, so we've had less sort of work in the yard space and even less work on how main lines and yards interact despite observed interactions. And I've got an example here looking at some interactions between two railway performance metrics. This is collected over a period here of a 1-year period. This happens to be for CN Railway. Back in 2017, they had a great example of showing over time, the course of a year, they had some network disruptions, and gradually over time, their terminal dwell time increased over the course of a year. And correspondingly, we see almost a mirror image in terms of the decline in average train speed over the measured week by week over the course of a year. So the top being average train speed and the bottom being terminal dwell. We can almost look at those two trend lines there almost as a mirror image of each other. And if we actually plot them against each other week by week, we get this amazingly tight correlation here for two sets of data that, again, are calculated completely independently between our average train speed and our average terminal dwell. So we can see here that we've got some sort of interaction, some sort of connection going on between these two different performance metrics. And the idea being that you can't focus on your terminals alone or on your main lines alone, but it's the combination of the two interacting that's going to govern your overall network performance. And at a higher level, we can look at the past just over 20 years. There's been several major network scale railway service disruptions that can be sort of traced back to this interaction between yard and terminal capacity and the main line, going back to the late 1990s when Union Pacific was merging with Southern Pacific and Chicago Northwestern. There was some overestimations of capacity of consolidated yards in Houston that led to some network disruptions. Again, in 1999, during the breakup of Conrail, there was some issues with estimating the capacity of classification yards and other operational changes that resulted in network disruptions. And finally, recently, within the past few years, there was some major operational changes with CSX where they're eliminating a lot of their classification yards or consolidating their classification operation. And that resulted in, again, some congestion and network level service disruptions as well. So the fact that this keeps recurring, suggests that we need improved understanding of our mainline and yard capacity interactions and a better understanding of how delay and schedule flexibility propagates through our network, which leads into our research questions that we've been looking at over the past few years here at the University of Illinois. So we'll move on and look at how these research questions map to different components of this network efficiency cycle. And so the first one we're going to look at is this idea of how does delayed train departures, or this concept of schedule flexibility in terms of our train departures, affect our mainline performance and capacity? So how does our mainline performance and capacity relate to our variability in train departure times? And sort of at a conceptual level, the idea is that this schedule flexibility creates uncertainty in the location of meets on single track. So the left time distance diagram here depicts what we would have on structured operations, where if we have a fixed meet time and a fixed travel time, we can predict with reasonable accuracy the time and location where those two trains going in opposite directions are going to meet. So that's sort of our structured timetable type operation. in a operation with schedule flexibility, we have a range of train departure times, we have a range of train travel times, and the resulting overlapping of those sort of two ranges of train paths is we have a potential range of meet locations and a potential range of meet times. And so the question is, when we start looking at this for multiple train paths over the network, how does this impact our mainline train performance in terms of delay and line capacity? So to investigate this, we've done some research with Rail Traffic Controller, which is a sort of an industry accepted standard simulation tool. We looked at some representative single track routes. And what we did is we set up an initial structured timetable where we resolved all the train conflicts, departed the trains at even intervals, so everything lined up perfectly at the sidings. And then we introduced schedule flexibility to sort of disrupt that initial structured schedule by adding in varying degrees of schedule flexibility, going from a fixed operation with no variability in our train departures up to plus or minus 720 minutes, or basically each train is randomly departing within each 24-hour period, is sort of depicted on the right. And you can see that we have a lot of uncertainty and overlapping in where our train meets would be falling relative to our siding locations. And when we look at the results over a couple of representative corridors, what we find is if we plot schedule flexibility on the horizontal axis and we look at our train delay, what we find is we gradually increase our schedule flexibility. We see for small amounts of schedule flexibility, we have a rapid increase in train delay. And then once we get above a certain point, we sort of have our train delay plateaus and flattens out. We don't see any further increases in train delay. And we see this both on single track with different numbers of sidings, and also on a denser single track when we start adding sections of double track to the route. And so we can take that, that information result relating schedule flexibility and train delay, we can sort of replot that for different volumes. And what we find is we can get delay volume curves that shift upward for increasing train delay as we increase our schedule flexibility. And if we go and set a level of service and define our capacity, what we'll see is that as we increase our schedule flexibility, our allowable volume or our capacity of our line decreases according to the those delay volume curves that are established for an amount of schedule flexibility on the line. So if we can replot that, what we'll find is we look at our schedule flexibility on the horizontal axis, we see that we have some decay in terms of our capacity when we have increasing schedule flexibility, depending on what level of service we set for our different trains operating on the route. So the idea is this variability in train departures coming from our yards and terminals is going to potentially decrease the capacity in trains per day of our mainline operation. So the next sort of research question is, well, what is the impact of these arrival delays, of this additional train delay, on our yards and terminals? So that goes to our second research question. So looking at the other portion of our network efficiency cycle, if we have delayed train arrivals, what does that do to our performance of our classification yards? So the tool that we've used to investigate that is YardSim, which is a hump yard simulation model that was developed by Optum. And it's a model where we can specify different operating and traffic parameters for a given yard layout of a classification yard. The model then simulates the movement of all the trains, switch engines, and rail cars as they cycle around the yard, resolves all the conflicts between those movements, and then provides us with detailed output data and a yard animation. And for this particular line of research, the Belt Rail of Chicago granted access to their YardSim model of Clearing Yard, which is a major hump classification yard in the Chicago area. And it's a complex operation with two directional inline hump classification yards. And for the purposes of our research, we focused on the eastbound classification operation. So that's trains that arrive at the west receiving yard, and then the cuts of rail cars are shoved up to the hump here in the middle of the yard, and then the rail cars are sorted into blocks in the east classification yard. And then we have a pull down operation that pulls those blocks to the east departure yard, where they're assembled into trains primarily for eastbound destinations from Chicago. So our experiments look at this eastbound operation, and we schedule or specify different levels of schedule flexibility or train arrival time variability, and examine what's the impact of that on the performance of this operation. So the experimental design, we kept the volume of the operation constant. We have a fixed number of blocks and arriving trains and departing trains that are evenly spaced throughout the day. And we introduce additional variation in the train arrival times, a similar process that we did on the main line, looking at the arrival time schedule flexibility, where 0 is a fixed structured operation where all the trains arrive on time, up to plus or minus 720 minutes, where basically each train is arriving randomly within a given 24-hour period. So when we look at the results, we could see some different hypothetical relationships between the average rail car dwell in a yard and schedule flexibility. If this was flat, there'd be no effect, and we could have a variety of different increasing relationships we might observe. When we look at our actual results, on the left-hand side here, we're plotting the average dwell time for cars in the yard as a function of our arrival time variability. And we see a somewhat similar trend to what we observed between the mainline schedule flexibility and the train delay, and that after we have some initial increase in our arrival time variability, we see an increase in dwell time, and then as we introduce further variability, it sort of plateaus. We don't see any further impact. On the right-hand side, we're looking at one of our other yard performance metrics, so the number of connections achieved in the yard, and we see sort of a mirror image of that, where once we introduce a little bit of arrival time variability, our connections drops off, but then as we further increase our variability, we don't see as much of we see a declining effect in terms of our impact on connections achieved in the yard. And so our dwell and our RCR2, or our rate car, rate train connections achieved, both have our greatest sensitivity to initial increases in arriving train schedule flexibility, and then further increases have a diminishing effect. So one other question just to extend to that research was looking at, well, once we sort of have that defined, the question is sort of to try and connect and wrap around the other portion of this network efficiency cycle is, well, what happens to that, that effect in terms of the inbound trains arriving at the yard? Does our classification yard amplify or dampen that schedule flexibility when we look at the outbound trains? And potentially the act of controlling that schedule flexibility, are we just translating that into train volume variability or train size variability, which has its own issues for the mainline operation? So to address those research questions, we took some of the same experimental results from the yard simulation and just analyzed them a little differently. The first was looking at our propagation of variability, and the idea was that we could compare our inbound and outbound train time variability for the different scenarios in the previous experiments. So the hypothetical relationship here at the top, we would look at our cumulative distribution of train arrival times, or our offset from our train plan time, and look at what the coefficient of variation of that distribution is. If we have no effect, and that yard, basically what we're saying is that the coefficient of variation of our distribution of a train arrival times would be very similar to our coefficient of distribution or variation in our outbound train departure times. If we dampen our variability, we'd expect to have less variation and a much narrower distribution of train departure times. If we amplify it, we would expect a much wider variation, or wider distribution or wider variation in our train departure times. So when we look at the actual results, the top graph here, what we're doing is we're plotting our offset from our scheduled arrival time and looking at our cumulative distribution. And as you'd expect, this pretty much matches our experimental settings, okay, where we have essentially a linear distribution across our scheduled arrival time. That's a function of how much schedule flexibility we're inputting in the yard. So that's something that we're controlling with our experimental scenarios. But when we look at our actual trains departing, what we find out is sort of regardless of what we put into the yard, we kind of get this same distribution of trains departing. Okay, we're roughly about 90% of our trains depart, somewhere between on time and 2 hours late, and there's a small percentage that potentially are poor performing trains that, for whatever reason, their assembly process just takes a long time in the yard, and they depart well after their planned departure time. And so what we find is that these departing trains exhibit somewhere between 120 and 180 minutes of schedule flexibility, sort of independent on what's being arrived in the yard. Okay, our departing train process is somehow largely independent of what the arriving trains are doing coming into our yard. And so what this sort of tells us is our classification yards act to both amplify low levels of schedule flexibility or dampen high levels of schedule flexibility to a relatively constant level of outbound schedule flexibility. The other interesting thing to look at is that this level of schedule flexibility, roughly corresponds to the amount that had the, that significant effect on the main line, where once we go beyond this, we'd see that sort of declining effect on our mainline operation.
Hey, Tyler.
Marty?
I'm not sure how explicitly you modeled inbound to outbound locomotive and crew connections. It strikes me that one of the things that would allow a yard to continue to function effectively and put out outbound trains in a relatively reliable way is if there was a slush fund, if you will, of locomotives available at the terminal, so that delays to inbound trains did not compromise the ability to build and depart outbound trains in a one-to-one power connection case.
That's correct. And so the model isn't tracking specifically all those interactions between the locomotives and crews, which are one of the sources of that or resource constraints on this network efficiency cycle. So that's a very good point, Marty. Okay. And our last sort of a set of experimental results is looking at the transformation of variability. So it's the idea is as we increase schedule flexibility, does our variation in terms of our cumulative distribution of outbound train sizes, does that remain consistent? Or as we increase schedule flexibility, do we also see a increase in our the width or distribution of our train sizes coming out of the yard? And when we look at our actual results, what we find is, even though it's a slight effect, as we increase our schedule flexibility, the width of our distribution of outbound train lengths actually does increase. And if we plot our coefficient of variation, we find this effect that, initial increases in schedule flexibility, we do see a greater distribution of train sizes coming out of our yard. Once we get above a certain point, we see a sort of diminishing effect. But the idea is these yards transform our arriving train variability into increased variation in outbound train sizes. And having these over length, potentially very long trains, introduces an additional sorts of variation for our mainline operation. Some previous research we've looked at, documents the delay and capacity impact of over length trains on our mainline operation. And then even if those trains make it over the main line, it creates additional variation for other yards and terminals. Okay, they're not consistently receiving trains of the same size. Now they've got to deal with very long or very short trains sort of unpredictably, and that affects the utilization of the yard track resources and has its own effect on the performance of other yards on the network.
Tyler, in this simulation, what assumptions or strategies were baked in terms of when a train was judged to be too small to depart and had to wait on cars for connection, and then what maximum train size was allowed?
I don't think there was a maximum on the train size. In terms of when it was departing trains, it was trying to make a balance between departing the train on time and maximizing the number of connections achieved in a way that sort of minimized the overall dwell time and throughput of the yard. So it kind of had a decision module that's sort of built into the model that makes that determination.
Thanks.
Okay. So those are some of the results of our experiment. And just to kind of wrap this back into our idea of looking at the overall network and not the individual components individually, let's look at the implications of this on a particular railcar transit time or a particular trip across our network. We can combine these mainline and yard results and look at some hypothetical rail trip plan. And so if we take our mainline train delay, our yard dwell times, and our connections achieved from our previous experiments, we can just look at this simple model here of a rail car moving from our origin terminal A across a number of mainline links through to classification yards to our destination terminal D. And you can use these concepts that have been around for a while, the concept of PMake and probability of making connections, to look at what the potential distribution of trip times are for this movement based upon the performance of the main line and the connection reliability of the different terminals along. Ideal case with no schedule flexibility, if we had a perfectly structured operation and we had low yard traffic complexity, in other words, the yards were we're making very few blocks, so they were at low utilization. And when we look at this, our input, what we can see is that we've got a very high probability of making an ideal type trip plan where we make both of our connections, and it takes roughly 68 hours for our rail car to move from our origin terminal A to our destination terminal B. Smaller probability of missing 1 or 2 connections and incurring a 24-hour or 48-hour penalty because we typically assume we have 1 train departure per day. If we take that same assumption of structured operations, but our yards become congested, we're making more blocks in them, what we find is that that distribution of potential trip time shifts off to the right a little bit, okay? Now we've got a lower probability of making our ideal trip time, and that ideal trip time has increased now to 71 hours, and we have a greater probability of incurring either a 24 or 48-hour delay. If we introduce our schedule flexibility, what we find is our mainline travel times increase, and our connection probability, each one of the yards, goes down even further. And we look at our potential distribution of railcar trip times. Now what we find is our most likely outcome is that potentially 45% of the time we're going to miss one of our connections. It's going to take us 106 hours to make that a trip time. And we have a almost nearly equal probability of actually making both of our connections, but still that's now going to be an 82-hour trip based upon the increased mainline travel time. And we still got, roughly 11% chance of missing both connections and taking over 130 hours to make this trip time. So it's an example here of how the schedule flexibility can affect both the mainline and our yards and terminals with a compounding effect that has a really significant impact on our overall ability to meet a trip plan and deliver a reliable and a prompt railcar transit time moving across our network. So just in summary, okay, so starting from a structured operation, we introduce schedule flexibility. That leads to increasing mainline delay and decreases our mainline capacity. That arrival time schedule flexibility is detrimental to our yard operation, and our yard operation is potentially going to propagate that variability, amplifying it or dampening it to a consistent amount of outbound train variability, and potentially transforming that into volume or train size variability. And when we look at an overall trip plan, our schedule flexibility impacts both the mainline and yard performance. And the fundamental idea here is that railway capacity is a network concept. Okay, so the main lines and yards interact to propagate congestion and poor level of service throughout the network. And so what's the implication for rail network operations? If we look at sort of these experiments, if we look back to our network efficiency cycle, we've had our existing body of mainline capacity research, okay? Through our first research, we've done some initial work to sort of document this connection between our yard departures and our mainline operation. Our second question and second line of research looked at the impact of the train arrivals on the yard, and then we tried to follow that looking at the propagation of these disruptions through the yard. And we've tried to get a more holistic picture of what's going on and documenting all the different components of this network efficiency cycle. And we feel this is very critical to understanding the overall performance of the railway network and how it responds to service disruptions and changes in rail traffic patterns. And we think this idea of sort of tracking schedule flexibility can help quantify our yard response to mainline effects and our mainline response to yard effects through this network efficiency cycle. And I think an important consideration is the classification yards can potentially act to disrupt our structured operations by potentially amplifying our schedule flexibility and volume variability in terms of train sizes. So what's the future? If we go back to our modeling tools, and the idea is can we use these types of concepts, taking advantage of new simulation tools and computing capabilities to remove those black holes at the end of our mainline models and our yard models and provide some links that can actually connect them? Can we have better connections between our mainline models and our yard models? And then when we look up at a network concept, can we take some of these abstractions and our fixed node costs and capacities and fixed link costs and capacities away and potentially come up with ways to wrap in our connected mainline and yard models into our overall network model? And I think that's sort of a research challenge and research frontier of how do we do that given some of the capabilities that we have now to conduct these simulations and incorporate them into the various types of nonlinear type models at the network type level. And that's an area where I think there's a lot of potential for academic research. From the academic side, we're always seeking opportunities to address specific real-world operational challenges and problems. But at the same time, we have some ability and latitude to conduct this sort of more fundamental and basic research into railway operations phenomenon. And I think the important thing, and the final thought I want to leave you with, is that industry partnerships are essential to moving rail research forward. Unlike a lot of other areas of engineering, it's difficult to bring an entire railroad into the lab, so to speak. We can only go so far with a representative network and corridor, and it's these intricacies of actual rail networks and operations that make for the most interesting and sort of fun, challenging problems to look at in the context of research. So what are some pathways for involvement? Posing real-world operational problems to academia is a great way for industry to get involved. Whether that's directly with a university or sponsoring, for example, the RAS problem solving competition or a student paper competition. Another way for railroads and industry to get involved is considering requests for data for analysis and validation. Obviously, there's anonymization concerns and wanting to protect certain sensitive data and things like that, but there's ways to work around that. And then the final thing I think is really critical is internships in network planning and operations at railroads and various other agencies. Every time I've had that experience of one of my students going out on an internship, they've always returned with a better understanding of real world problems, the constraints, and how railroads actually use these tools in practice. And that typically leads to two things: better formulation of research questions, because they know what better questions to ask, and also more applicable results. So this tends to be a real win-win for both the industry and academia. Industry has a student that's already been trained and is going to be a great future employee. And for academia, that's one way to import some of this railroad domain and industry knowledge back into our research programs. So with that, I want to thank you for your attention. I also want to thank really quickly the technical collaboration assistance we've had over the past few years of looking at these different research questions from the Belt Rail Chicago, Optum, Berkeley Simulation Software, and initially CSX on starting some of this research. And over the past few years, this research has been supported by the National University Rail Center, which up until recently was a US DOT Tier 1 University Transportation Center, and also tremendous support we've had during my entire tenure at the University of Illinois from the Association of American Railroads. So with that, again, thank you for your attention, and thanks to Nicola for hosting that. And I'll be free to answer the questions you've got queued up at this time.
Yeah, okay, great. Thanks a lot, Tyler, for this great comprehensive presentation. It was really, really good to see that you are combining things together from yards and main lines. And we had quite a hyped discussion at the chat as well. And we also collected quite some questions. So I would start with a few. From Carl van Dyck on theoretic maximum line capacity. So compared to theoretic maximum line capacity, what would you estimate the percentage of this capacity is achieved given a target level of service? Be 60, 70, 80%? Could you comment on it?
Yeah, and that's something that's very debatable, but I feel like that that 60 to 70% range is something that's quite a number that most people are typically comfortable with in terms of what the practical capacity would be relative to the ideal perfect case where every train's traveling at the perfect speed and all the meets and passes line up on that perfect return grid or the perfect pool type model for single track operations. So I think I'd agree with those type of numbers based upon what we see when we start introducing train heterogeneity in terms of speed, performance, and irregular passing sidings and other disruptions to the mainline operation.
Yeah, and more practically, if you had a hand on real traffic realization data, do you see some support for these numbers, or is there more to work on and we still need to experiment more?
I think I'll answer that a couple of ways. If you look at some of the available parametric capacity models that we have that were developed based on North American Railroad, and that primarily being the model that CN developed in the 1980s, based upon their real world data. There's definitely an effort to come up with some new parametric capacity models that have additional capability and make additional considerations that weren't really considered at the time, in terms of like additional speed heterogeneity between trains and running overlaying trains and things like that. So I think there is a need for improved parametric type capacity models based upon actual traffic data. The other thing that we were fortunate enough to, some of my colleagues here at the University of Illinois were fortunate enough to partner with CSX and get a large amount of traffic data and do some interesting machine learning type applications where they were looking at trying to predict train arrival times. And it was amazingly complex problem. I think we all sort of underestimated all the variation, all the things that could go wrong, and how those would potentially influence and cause all these models to have real difficulties in predicting something as something you think is simple as when a train is going to arrive at its final terminal. So I think the need for actual data and additional research to look at what we can do with that data is there on both main lines and yard operations.
Yeah. Then I have another one.
Nicola.
Yes, Milan, please.
Actually, this is the question about the practical and ultimate capacity. In aviation, there is the clear concept what practical and what actual or ultimate capacity is. If trains are arriving exactly at time, and if there is maximum trains separated by the minimum distances or the minimum time, that could be called ultimate capacity. If you set delays, and then as you show very, very nicely on your first let's say, slides, then you get so-called practical capacity. That means train throughput given the average delay per train. So these concepts are very clear, and I think if it is asked about, then it should be asked about two capacities, and the ratio between them is actually utilization of the rail line or any service system, let's say utilization of ultimate capacity, practical ratio between practical and ultimate. That means practical is sometimes 80% or 90% of, let's say, ultimate, something like that. But I see that these concepts are present also at railways, like in the very similar way are present in the aviation for a long time, So you have airports delivering their declared capacity. So declared capacity is actually ultimate capacity. That means given conditions. That means we specify the capacity of a railway line given the conditions. What these conditions could be is something that we need to specify. And in practice, this is practically carried out. But I would have maybe a question about that, about flexibility and strict scheduling of trains. As I understood well, but please correct me. Flexibility worsening the performance of the rail network or the cycle. Is that true or not? Flexibility is not good.
Yeah, that's sort of the underlying
I understand
theme
that well.
Yeah. So the idea is if you could plan everything and execute things perfectly, you could turn this cycle faster, have rail cars and resources moving it through, and potentially reduce the overall number of rail cars and locomotives and crews required to execute the plan. But as soon as you start introducing variability, whether that's due to some disruption or you intentionally introduce variability by holding a train to make connections or some other reason, allow for track maintenance or something like that, you start requiring additional locomotives, additional rail cars, and additional crews and resources to handle all that flexibility and the potential of getting off the plan and deviating it, and that overall, again, causes you to need to have a capacity of your operation which is below that sort of ultimate theoretical, perfect capacity, and then lower it down, as you said, to a certain degree of utilization, which is sort of defines a practical capacity for a given level of service.
Are you going to extend your research also on these aspects you have just mentioned? That means improving, that means reducing the resources used, energy consumption, impact on the environment, and these kind of things. I think this is the very good, very nice basis for getting the complete picture about how the railways operate and contribute, let's say, for the increasing sustainability of the freight transport system in the US.
I think that's a long-term goal, and whether that's me and my students or collectively railroad academia coming up with these models, I think that's a good goal in terms of where we need to go. And there's sort of efforts to keep building on and adding on and eventually come up with what's that ultimate model of the entire rail network that we can make the changes that you've described and come up with the best plan that optimizes the rail operation from a number of different fronts.
Can I make one observation on that, which is there are what I would say at least three or four different operating models for freight railways. You got the North American model, have what I'll call the Western European model. You also got the former Soviet Union and China model, which is both flexible yet has very good resource utilization and velocity, because it very much focuses on having multiple departures per day for every block, which effectively is part of the equation in the yard dwell time formula that is not really been spoken about too much, but is very important relative to the North American model. And then you have the conveyor belt unit train operations like you might see in Brazil or Australia, which have another operating model. So there some of those, other than the European model, none of those are working on fixed train schedules. So they all have, quote, schedule flexibility, but they take different approaches particularly to line utilization, where the schedules and the meets and passes are pre-planned. You may change what train operates in which slot, but you're still trying to hit a very tight schedule process, and you're trying to make your trains more homogeneous in terms of speed and length.
But
thanks a lot.
Can I ask the question, do you think that this approach which has been presented is applicable also to the models of real models of operating the railways you have just mentioned? Is that sufficiently generic, or the modifications are needed in order to be applied?
I think the principles are the same, and so they are applicable, except for the unit train case. But the performance parameters, and there are assumptions built in that would have to change the way this model is applied to other areas. I don't know if Tyler agrees, but that would be my perspective.
Sorry, interrupting.
Okay, so I have another question. So is there any effort from your side, or that you recognize among researchers and industry, to rank causes of planned deviations, both in frequency and impacts? And yeah, some examples like crew shortages, power shortages, or broken down locomotives, block complexity.
Yeah, that's an interesting question, and I think there's an excellent report that was done for the Association of American Railroads by Carl Martland a few years ago. We cite it quite often in our papers, where he did an extensive a survey of various people in industry and looked at a lot of data and tried to look at sort of a root cause analysis of what was causing a lot of freight train delays. And he went through there, and came up with a bunch of rankings and figuring out which some of the most important factors are. So that research, there's a very documented report that looks at that. One of the other interesting things is the research I talked about earlier that in cooperation with CSX, where they were developing some machine learning models for train arrival time predictions. From those models, they were able to sort of identify through some of the regression techniques of what were the most important factors in terms of predicting the train arrival time, which translates into what are the most important factors that were causing delay. And it was very interesting that different portions of the route, depending on the route topography and the train density and the layout of the track, you'd have different factors where different, had varying levels of importance for the mainline operation. We've done a little bit of in the yard type operation of trying to look at the sensitivity of these performance metrics to a variety of different inputs, not just the schedule flexibility, but the volume variability, changing the number of blocks, changing the volume, changing the sort of fit between the distribution of blocks and the track lengths, and trying to look at how all those factors relate to the yard performance. So, so there's some of that done in the literature. There's some of that we're sort of actively doing, but I think there's a lot more that could be done as well.
Great. Thank you so much.
May I add something? Nicola, may I add something?
We are at the end, so if it's super short.
Simply to suggest one sentence. Is it possible to set up the systematic monitoring of the performances of the railway freight transport in the US, and to have indicators of the service quality and other performances? Like there is the similar system like airline quality rating of US airlines. Is it possible to carry it out for the railways too, and systematically monitor during certain periods of time how the railways perform?
So Tyler, if you can come up with a yes or no answer, that would be great.
A yes or no answer could be potentially dangerous to that, but a good example of this would be the Chicago Transportation Coordination Office.
Initiative for the further research.
Right, but looking at Chicago Transportation Coordination Office, that's sort of tasked with doing that on all the railroads going in and out of the Chicago terminal to help keep that terminal fluid, and where they're tracking performance metrics, and they're having regular meetings between the different railroads and trying to preemptively prevent some of the types of congestion that, the example I showed earlier on the CN result. I mean, that was primarily a result of large snowstorms and then things snowballing through the Chicago terminal that resulted in that behavior. So I think there's precedence for that. Could it be improved? And that we're dealing with private enterprises, and so that's a question. They are required to report certain performance metrics. Could those be improved or supplemented with different metrics? That's a question for the industry, but there's some precedence of them using these types of things to coordinate and improve operations in very critical areas, such as the Chicago terminal.
Okay, great. Anyway, thank you so much.
My compliments for your presentation. Typical engineering presentation. I liked very much.
Well, thank you. I'll take that as a compliment.
Great. So I would like to thank you all for joining and actively participating in the presentation. We still have quite some questions unanswered, so I invite you to contact Tyler directly or myself, and we'll forward the questions to Tyler. And hopefully I expect to see you again soon. So we are formally done, and since Tyler is so awesome, he has some more time available after we close this session. So if you have some more burning questions, or you want to catch up with him, feel free to do so in the next couple of minutes. But from my side, that would be all. Thank you so much, and I wish you a great day.
Javite se na Skype.
All right. Well, thanks, Nick.